this video, we are going to discuss about Unit 5, Interfacing Microcontroller. Under this, we have 8051 timer, serial port programming, interrupt programming, LCD and keyboard interface, ADC and DAC interfaces and sensor interfaces, external memory interface, stepper motor and waveform generations here. Now, in this video, I'm going to concentrate on DAC using 080. Okay, so let's go for the connections. The required components for this is microcontroller. We have used AT89C51 or otherwise we can go for 8051 also. And then DAC kit, which is named as DAC0806, and then resistors, capacitors and op-amp will be there. Output of the op-amp will be obtained here and that will be given to CRO. Okay, now let's see the circuit diagram. So on the kit we'll be observing this block over there. The first one will be here. We will be taking the first diagram as DAC kit 0808. So this is the DAC kit. The pins of output A1 to A8 pins, output pins, pin number 5 to 12 are connected to, this is the microcontroller, controller pins of 1 to 8. That is port 1's 0 pin to 7. So these are the pins which we are taking. So the connection extends like this. Pin to pin connection is given, and then output pin will be pin 12 here. Okay, so output pin will be taken to, one of the output pin will be taken to the op-amp's input, which is mentioned as IOUT. Okay, and then after the signal enters into the op-amp and it will be converted into waveform, here we'll be getting the Vout. The Vout is given to CRO. So this is the CRO where we'll be observing the waveform. Whatever code we write for the microcontroller, that type of waveform will be generated here. If you write code for square wave will be generated. If you write code for triangular wave will be generated. If you write code for sawtooth waveform will be generated. And if you go for some miscellaneous designs just like this, we can start writing the code. Okay, or otherwise we can have different types of waveforms, which I would like to give it as assignment. Like this also we can try it. See that the minimum value is 00H and the maximum value is FFH, and here you can take it as 1F, here you can take it as 6F, and you can give the shape. Likewise here you can go for 0, and this one is 6F, and here FF, something like this. We can take the points. Okay, now let's go for the physical hardware connection. This slide shows you the physical hardware connections, and then this is the kit which is considered as microcontroller 8051, and this is operated, the inputs are given to the kit using the keyboard, so that we can see the coding here. It stores the coding here, and then these are the bus connections extension given. Using this bus cable we will connect the DAC kit. This is the DAC kit DAC 0808. This is the DAC kit. We'll interface the cable here, and then it is connected to this. So this is the interfacing procedure. And to view the output, here we have positive terminal and negative terminal. Here if you identify, some indication will be there as positive, negative. Using the CRO probe, we connect this starting point of the CRO probe to one channel, and the positive negative terminals, red shade cable is connected to positive and the black one will be connected to negative of CRO. So this goes to the one of the channel of CRO. On the CRO, you can observe triangular waveform according to the code or square waveform. Okay, so this is the physical hardware connection for the interface. And now, um, okay, so we'll be observing the waveform on the screen, which I already explained. And now let's go for basic requirement. See, subsequently, for obtaining the desired frequency on a square wave, we have to manipulate the delay. Okay, that is, uh, if I want the square wave form like this, the line extension is considered as delay here. Based on the delay, you'll get this width. So if I have more delay, I may get this type. If I have particular delay with the less delay, this is with less delay, this is with more delay. Okay, so that point how we need to discuss means, based on this, we know that machine cycle frequency is 1/12th of the crystal clock frequency. So with the crystal clock frequency of 11.0592 megahertz, the machine cycle machine cycle frequency is 921.6 kilohertz. Okay, so to sum up, we'll be getting as 1.085 seconds. So this is in frequency, this is in time. We know that f will be equal to 1 by t. So based on that, we can calculate what should be the timing. So if I want 1 kilohertz square waveform, then we need to inverse it. So we'll get it as 1 milliseconds of time period. Okay, this is taken as 1 millisecond actually, the delay time. So we need to use for 1 milliseconds, 461 machine cycles should be idle. That is, this is nothing but idle case. Okay, this condition is taken. Once we give the output as 1, after that it should be idle. So during that idle period, the line will be extended. Logic 1 will be extended. So how many cycles it should be idle means 461 cycles it should be idle. So which is producing 50% duty cycle. Okay, that is 50% means logic 0 and then logic 1, 50% duty cycle. Okay, so let's go for it. Let's go for the coding. uh, this coding represents, we are directly taking the ports of 8051 directly and using that we are generating the waveform. So the conditions are, we'll take interrupt enable here. Okay, and the timer 0 is kept in mode 2 at port 1.3, so using interrupt mode, and then so that we can have 10 kilohertz frequency. And then port 2 we have as A and B is at port 0. Okay, and then the crystal clock frequency is 22 millihertz and waveform should be 10 kilohertz. What should be on off time means 50 seconds. And what about the timer? The timer is taken in mode 2 and it is 8-bit auto reload mode. We have 91.66, that is 92 machine cycles are required here. For that we have TH0 and TL0 will be loaded with 164. Okay, so we'll observe that here. First, as we discussed, T mod is taken as 02H and then port 1 is 00, interrupt enable is 82H, and then TH0, TL0 is 64 value 164, and then set the timer. After that we'll go for waveform coding, ljump wave, where the coding is written here, clear TF, and then send that to output port. Okay, P13, that is interrupt enable, will be executed, then return to the interrupt. Okay, where is the interrupt occurred? We got it here. So this interrupt goes on executing, and then meanwhile, what about the delay case? The delay case is observed here. Okay, keep doing. The value of port 2 is taken and B value will be taken here, and just it goes here. This gives the delay here actually. Okay, so like this the waveform is generated using 8051 ports. Now let's see if we interface 8255 to 8051 microcontroller, and we can connect a DAC kit also. The coding goes this way. So here the main idea is first send 0 and then produce the delay, and then after certain delay send ff means it is high value, logic 1 value. After sending high value, produce the delay, then after certain period again send 0 0 and then produce the delay. So this is the actual intention, so that we can generate square waveform. So initially we'll initialize the control word here, control word of 8255. Okay, control word of 8255, the address is given here. This is the address for control word of 8255 and port A address is taken. 80 means according to the control word format, we'll take all the ports as output ports, and the format is in IO mode format, not in bit reset format, it is in IO mode format. Okay, control word value is taken into A and control word address is taken into DPTR. Transfer that value into DPTR. Okay, and then as I already told you, 0 value is sent to port A, and then after sending we'll go for call delay. Then uh, after that we need to take here, actually it should be FFH. After call delay, FFH, and then send that to port, then call delay. What about the delay program? This SGEM start means the program is continuous, so the waveform goes on continuously like this. What about the delay program? Here we have written the delay program separately, just to kill time. The programming is done here, so that we will be getting this. Okay, so just take some value in R0, R1, R2, and then just decrement that, execute it until it becomes 0. First loop is executed, then decrement R1 so that second loop will be executed. This loop will be executed, and finally the third loop will be executed. So this way the loop is produced. Finally go for return. Wherever the delay program is